Fun fact! Did you know that a mass bouncing on a spring precisely traces out a sine wave over time? Want to know why? Welcome to Myki's Math Show and Tell. Watch this. Believe it or not, the motion of a satellite in a circular orbit is a very close cousin to that of a mass on a spring, and by looking at and comparing these two types of motion, we can prove our statement without using scary maths like calculus and differential equations. In fact, I bet I can explain it using nothing more than simple high school algebra. To begin, we'll consider the forces happening in each scenario. Let's take Hat Duck, my lovely OC bungee jumping. Suppose he's hit the bottom and he's now bouncing up and down with the cord always remaining straight. The cord is now behaving like a Hookean spring, meaning the total force on him by definition behaves like this. The direction of the force is always towards the midpoint of his oscillation, and the further away he is from this midpoint, the greater the force on him is by a constant factor. In other words, the force on him is directly proportional to his displacement from the midpoint. This will be very important later. Perfect. Let's now put him in a spacesuit and launch him into a uniform circular orbit around the Earth. By definition, if his orbit is uniform and circular, then gravity is the only force acting on him, and the size of this force doesn't change, only the direction, which, as you would expect, always points towards the center of the Earth. Here's where things get really interesting. Let's freeze time for a moment and take a look at this force. Something really cool about forces is that you can always take them apart into components in different directions that, when applied at the same time, do exactly the same thing as the original force. For instance, gravity is pulling on Hat Duck this much and in this direction, but this can also be expressed as the force pulling him in this direction this much and in this direction this much at the same time. Exactly the same thing. Here's what the orbit looks like with the force shown as these components. Now, again, by definition, if Hat Duck's orbit is uniform and circular, then his vertical displacement must trace out a sine wave over time. Let's consider just his vertical displacement and the vertical component of gravity on him. Notice how his displacement and the force on him are directly proportional to each other because they're both a given constant times sine theta. Starting to look familiar? That's right. The nature of vectors, along with Newton's second law, state that only the component of the force on an object in a particular direction is able to influence its motion in said direction. In other words, if we take away the horizontal components of displacement and gravity on Hat Duck, we're still left with a valid system. And notice that this system is exactly analogous to the bungee cord one. In both, displacement and force are directly proportional, and we now know from earlier that this motion must be sinusoidal. And there you have it, proof that masses on springs bounce sinusoidally. This has been Myki's Math Show and Tell. Thanks for watching!